Now to the technology showcase. We're going to see presentations on technological building blocks which are expected to be instrumental to the realization of space resources utilization and sustainable exploration. Going to cover a range of topics, including the use of AI for resource characterization, regolith simulant development efforts, and resource extraction techniques. This session is going to be chaired by somebody who has been here from the start. You will know him from the talk yesterday. It is Advenit Makaya, an advanced manufacturing engineer at ESA. Please welcome Advenit to the stage.
Thank you very much, Lisa. Thank you for coming back for this session. So we'll have to start with two speakers from the Norwegian Geotechnical Institute. And the first one is Luke Griffiths, who will tell us about using digital twins to bring geotechnical testing to the lunar surface. Welcome, Luke.
Thanks for the introduction. Yep, so I'm delighted to be here. Thanks to the organizers for the opportunity. I'll be presenting together with Alex Jerves how we're using at NGI, Norwegian Geotechnical Institute, how to use digital twins to bring geotechnics to the lunar surface. I'm Luke Griffiths, I'm a geophysicist, and this is also the work which results from collaboration and efforts of the colleagues I've listed on the left, and this project has received funding from the Norwegian Space Agency as well as the Norwegian Research Council. Yeah, and just to start, a bit about NGI, because perhaps we're not known to everyone here. So we are Norway's largest geotechnical specialist community and a leading international center of research and consultancy in engineering-related geosciences. So we conduct applied research and consultancy across four main areas, which include offshore energy, natural hazards, geotechnics and environment, and geodata and technology. And that includes our labs, field investigations, and our instrumentation departments. And so the whole aim is to research and develop solutions for industry and society, ensuring that we live and build on safe ground. And so the heart of NGI has been its labs historically. And that's the case today. We have labs in Oslo in Norway, in Houston in the US, and very soon in Perth as well in Australia. So these are very large labs that are capable for doing industry scale testing campaigns, for example, for offshore wind farms. But we also have a very advanced kind of R&D capability. So we have the capacity to innovate and develop new methods, techniques, and equipment. I also want to highlight that we administer the Norwegian geotest sites. These are for testing field equipment, like geotechnics or geophysics. And one of these actually is in a permafrost site on Svalbard. So if you're interested in testing equipment in icy soil, then please do get in touch. So why geotechnics on the moon? So humanity plans to explore, build on, excavate, and process the soil or regolith of the lunar surface. And how our tools and structures interact with the regolith, this all depends on its geotechnical or its mechanical properties. However, we've only been to some locations on the moon. We only have a small amount of sample material. We've done a few experiments, and actually lunar geotechnics remains a really key knowledge gap for ISRU. So this slide is just to give an idea about the subsurface on the moon and what we're talking about here. So for ISRU, we're interested really in the top 5, maybe 10 meters depth. So we're very shallow, and this is important because it means that we only actually have a low amount of overlying sediments or forces acting on these sediments and from the surrounding sediments at these low depths. So we're actually dealing with very low, what we call stress applying on the material. And this is a key parameter for determining its mechanical properties. So this is very important. I just want to note this. And of course, on the moon, the gravity is less than on Earth, and so this stress is even lower. And because this is such an important parameter, it's very important when we're testing these materials that we're doing them under stress conditions which are relevant to the moon. Just want to highlight that. So now for the lunar regolith itself. So most of the current data we have comes from the past Apollo and lunar return sample missions and the in-situ data they collected. So we see here an image of one of the astronauts doing some kind of geotechnical site investigation on the lunar surface. And just on the top right, we have an example of one of these agglutinate grains where we have this impact melt, which kind of sticks together, solidifies. And then because of the lack of erosion, or at least as we know it on Earth, these kind of stay intact, and we have these very peculiar grain shapes. Along the bottom images, we have recent material returned from the Chang'e rover, which are kind of like impact melts, which are then solidified, and they form these like spherical beads, which can also have agglutinates on around them, which you can see on the bottom right. So we have a very interesting material we don't have so much of, we don't know much about it. We're seeing that it's increasingly quite variable. And so upcoming missions will provide new data and new samples that we need to kind of learn from. So how can we kind of maximize the information return? So for now, what we propose is focusing on improving the geotechnical characterization that we do in the lab on regolith simulants, which is designed to reproduce certain aspects of the lunar regolith, before testing this material that we actually get from the moon using these techniques we've developed. So I won't go into all the details here, but this is just an example of some of the geotechnical testing we've done on the LHS and LMS regolith simulants. We just have some of the microstructure in the top left there. So we did like a combination of index tests, so all like characterization of the materials, and also advanced tests, which are kind of determining the mechanical behavior. And so you can see the equipment we used to do this. So this is kind of much more advanced, I'd say, that more exhaustive than what is generally done for lunar simulants. Yeah, so I'm just going to focus on one of these points, which is the density of these the materials. So what I'm showing here is the dry density measured on samples of LHS and LMS simulants in black, and then on the actual lunar regolith from the Highland and the Mare in red. So the closed symbols are the densities of the material in its loosest state, so the minimum density, and the open symbols are the maximum density. So these are very important parameters, because basically when you have your soil, it's going to be somewhere between these two states. And where it is between these two, this kind of relative density, that really defines its mechanical properties. So if you get these wrong, then you don't really know how densely packed your material is. So it's a very simple parameter, but it's a key one. And what this shows, this is part of a study that's led by Santiago Quinteros at NGI. And some of the key takeaways we have here when compiling and acquiring these data. So I didn't mention, actually, these are from different labs and using different methods. So when we have these different methods, we see that there is some scatter to them. So it seems like we have some kind of variability between the materials. But actually, we're dealing with the same simulant, so they should be the same. So it kind of just highlights the kind of method dependency that we have. And it's really important to document the methods and explain how it's been done if we're actually to compare data sets. We also see that there's some kind of fundamental differences. The min and max densities of these simulants are quite different to the lunar regolith. And so this will affect the actual kind of inferred geotechnical properties of the regolith. So to kind of summarize and the kind of takeaway here is that we should really be trying to share experience, testing methodologies, and data if we'd kind of understand the data we already have and be ready to integrate new data as it comes in. So we wanted to look a bit more detail about why we have these differences in behavior between the simulants and the lunar regolith itself. And so for this, we were lucky enough to get a data set from the National Institute of Standards and Technologies in the US, or Nist, from the Apollo 11 and 14 missions. So these are nano-CT data. We also required some nano-CT images of the LHS and the LMS simulants in Oslo. And then we were able to determine or create these kind of digital avatars of the grains from these. And you can see in the three example grains here that you have this, you can see like the kind of like agglutinate materials which are kind of stuck on the outside of the grains, and we have these intragranular porosity as well. So very interesting shapes. And we can actually take these grains and we can calculate a range of kind of morphological parameters, so like a description of the grains. And this chart shows the different, 6 different shape parameters that we can calculate from these grains. And each of these are taking like thousands of digital grains to calculate these distributions. And I'll just focus on a couple of them. So first, in the bottom left, you have the diameter of the grains, so like an equivalent diameter. And we see that the kind of distributions of these, it lines up quite well, which makes sense because the simulants are made to follow the particle size distributions of the lunar regolith. However, if we look, for example, in the top middle at the aspect ratio, we see that there's a shift between the distributions of the Apollo 11 and 14 samples and the LHS-1. So it actually means that the LHS simulants, they're kind of longer and thinner, relatively speaking, than the Apollo samples are. And we can this may be due to like how it's been made compared to the formation of these particles on the moon. So it's like through breaking and crushing of grains, so we might end up with more elongated features. Whereas on the moon, you have these agglutinates, you have melting, solidifying. So yeah, different processes may mean that we have these different shapes. And I think it's really important to know that just a particle size distribution isn't enough to characterize the material. These other shape parameters are very important for the mechanical behavior, and so it's really something that we should look to determine for simulants. So I've spoken a lot about the grains, now about the lunar environment itself. We all know it's very different on Earth. We have very low pressure, low humidity, low gravity, and extreme temperatures. And these are very challenging to reproduce in the lab, although I've seen some examples of some quite impressive lab facilities where they go a long way to doing this. But how do we account for these very challenging conditions and these, and how do we try and relate our lab tests that we do on Earth to the actual lunar surface? And the answer to that is to use a digital twin, which I'll pass over to Alex, who should be online to present this.
Can you guys hear me?
That's good, yeah.
Can you guys see me? Hello?
Yeah, that's good.
All right. So thank you, Luke. Next. Here, as we can see here in the video, we have created the first one-to-one digital twin ever. So from CT, X-ray scans, nano and micro CT, we have acquired images that have helped us to build digital versions of those grains, mathematical digital computational versions of those grains. The shapes, the positions, and the orientations of those grains within the original sample, and recreate an entire sample digital twin with every single grain from the real sample occupying the space, the orientation, as in the original one. So once we have the sample and all the grains, positions and orientations, we need to calibrate the internal parameters of the model that we are going to run with these digitalized grains, with these mathematical representations that allows us to perform the simulation. We calibrate those internal parameters of the model with respect to the experimental results from the original sample. And once we tune that, we can perform simulation on that sample, the digital twin, again and again under different conditions, including low gravity, high pressure, and different multiphysics like grains breakage and so on. So we have created the first one-to-one digital twin using a sample of oil sand from Norway. Next. Here we have a toy sample with only 3 grains, where we have combined 2 methods, the 3D LSDM, level set based DM, that allows us to account for the grain shapes, and also finite elements that allows us to model the heat transfer, the time-dependent heat transfer, heat conduction among the grains. So this is a multiphysics and a multi-body problem. And we also include the capability of the grains to dilate, to swell due to the thermal changes. And on the right, we can see the stresses that these grains dilations are or expansions create on the container's walls that cannot be seen here. So all of this can be done. Next. We can also include something that has been found to be really, really important, especially on the moon surface, which is the electrostatic induced cohesion among the grains, which has been shown to affect equipment and the fabric from the astronauts' equipment and so on. So it is really important in this case. And we do that by including electrostatic effects or electromagnetic effects between and among the grains, adding surface charge densities with different signs and computing those electrostatic forces in the neighboring grains. So as we saw in the video on the left, with a toy sample, 3 real grains charged on the surface very differently, it works perfectly. Next. Finally, we have next this example where we can compute physical properties such as the angle of repose. And as we can see here, we can virtually reproduce this real test from the lab with a sample from the Apollo 14 mission, 3,500 grains more or less, and we can change the gravity. And once we change the gravity, we see that the angle of repose goes higher and higher. So from around 20 degrees from Earth's gravity to nearly 30 degrees to the moon's gravity. So there is a gap, there is a difference of 10 degrees, which makes a difference in the behavior of the material, and has been seen in the moon that they have these very vertical walls, nearly completely vertical walls, due to high cohesion, high friction between the materials, and also the low gravity. So it is really important when it comes to the behavior of the materials themselves. Next. So,
yeah,
look.
Yeah, just to summarize then, so geotechnics is crucial for the success of safe and sustained lunar exploration. And we need to work together and share data and communicate our methods. This can be via joint research projects, consortia, communities, and data repositories like ESRIC's knowledge base, ESA's sample analog curation facility, and then Colorado School of Mines regolith simulant database. So these are really key things that we need to make sure these are up to date and we're contributing to. And then given the current challenges, which are lack of material and experimental data under lunar conditions, numerical modeling and digital twins are really key to bringing geotechnics to the moon. Yeah, so just to finally mention that if you're interested in collaboration or consulting on geotechnical topics and related to lunar exploration, we're very much available for that. So there's possibilities that we can host students at NGI to work in the lab, to participate in research proposals, provide laboratory testing services and things like this. And for more info, please stay tuned in as we have some, we aim to publish these results that I've shown you today with some of the advanced tests as well. Yeah, thank you.
And Alex. And our next speaker is someone who is well known in this community and in the new space community. It's Acierno from OffWorld, and he will tell us about OffWorld celestial and terrestrial swarm robotics and ISRU system. Welcome, Kyle.
Good morning, everybody. It is a pleasure to be here. It's really incredible. You know, I came to one of the first sessions that they had about 5 years ago, and it was just a small group of 10 or 20 people, and now to see such a young, dynamic, multicultural group of people attending this conference, it's really inspiring. So really pleasure to be here, and thanks so much for the government's continued insistence on investing in this and bringing people here. Really, really grateful for the opportunity. So today I want to talk to you about OffWorld and about the AI-powered industrial workforce that the company is developing. How OffWorld is a full-stack innovation powerhouse from ideation to execution. And I want to share with you today some of the things that we're doing. First and foremost, this has to be said that potentially in the next few hours, potentially at 420, on 420, a revolution will happen. And this vehicle is going to transform the way that our industry works. It's going to allow us to start to build colonies in space. And to develop colonies in space, we need colony technology. That's what OffWorld is working on. We're looking at highly collaborative, interoperable, robotic colony developers. These machines are modular, they're autonomous, and they're able to do things that humans cannot do. We really want to work to try to keep humans out of harm's way. But as that vehicle hasn't flown yet, we really need to focus on Earth first. We need to focus on the market that exists and trying to develop that technology terrestrially first. When the company was thinking about this, we saw a number of different opportunities, whether that be in airport operations, landfill processing, maintenance and repair, or most importantly, I would say, mining operations, just because of the size of the market and also how that technology can be applied both on Earth and then ultimately in space. And when you look at the entire mining cycle, there's a few things that need to be done. At first, you need to have a robot that can do surveying or prospecting. Then you need something that might be able to weaken the rock. And finally, something that's able to then apply some technology to take that rock away from the mine itself. So first robot that OffWorld was working on is called a surveyor bot. And this surveyor bot is able to essentially operate in extreme environments to do surveying and mapping. So again, from ideation to execution, here you can see the surveyor bot that's in operations. We've deployed this in mines around the world already, and the team that's been working on it just did a fantastic session. Just a really smart bunch of guys that were able to get this into motion. Next to you, you have the microwave bot. Now this robot has been deployed in South Africa into a platinum mine, and I want to show you it in action. So this microwave is basically able to precondition with rapid thermal shock. And that produces these micro cracks, which then allow the rocket to be weakened by about 30%, which reduces the wear and tear on the equipment and allows the rock to be then removed quite easily. But okay, then you need to remove the rock. So OffWorld went into the laboratory from ideation to create a digger bot, which will have not only a saw, but also a chisel. They put their heads together, they developed this, deployed it into a mine, and then demonstrated the capability to work fully autonomously in a mine to, again, as you can see here, saw, and then on the right-hand side, you can see the chisel working. Now, this is a little bit of what it looks like towards the end. You can see these slots, which they have developed, which allows for the chisel to then do some pinpoint precision mining. That allows the operations to be reduced significantly. You can then pull out that material in a much simpler way. All this then allows for us to take that technology that we've developed here on Earth, not just the machinery, but also the AI brain on top of it, and then apply it to the lunar surface. And that's what we intend to do. We intend to then deploy these robots on a starship and then start to demonstrate it as soon as we can. We are very happy to announce yesterday that we have signed a multi-year program with the Luxembourg Space Agency to develop the technologies that will build upon what's being done in the United States, but here in Luxembourg specifically, to build a processing unit which will be able to take some of the regolith from above ground or potentially even below, process that, and then create lunar hydrogen and lunar oxygen that will be extremely essential for people who are going to be living on the lunar surface. Now, obviously, the surface of the moon is an extremely difficult environment to survive in. So if we can't do something above ground, we need to change our environment, and potentially we can do it below ground. This is an idea that we have to develop an entire mining operation in a lava tube or in excavated material that we have developed underneath the surface of the moon. So OffWorld is a company that's continuously expanding. We are developing operations in the United States, in Luxembourg, in South Africa, and in Australia. We have people here from most of those places, so please come over, have a look at us, and be a part of our evolution. This company is continuing to grow at a rapid pace. The leadership has really brought the company an extremely far way, and now that we're developing our roots here in Europe, teaming up with our partners at the European Space Agency, with the Luxembourg Space Agency, and ideally with many of you in this room, we just look forward to working with you in the near future. So thank you very much.
Before we move to the next speaker, Alexandre Meurice this morning could not show his video, so he has time now for that.
Thank you. Yes, so for those who missed the presentation this morning, you have a good recap in this video of what we do today, what's going on in China in the next 5 years, and the long-term vision of Origin Space Company. Thank you.
So that was Origin Space. And now back to the program for this session. The next speaker is Aliz Zemeny from the European Space Agency's ECSAT Center in the UK. And Aliz will tell us about Lunar Highland simulant selection and the Lunar Analogue facility. Aliz, you're welcome.
Hello, everyone. I'm Aliz Zemeny. I'm a volcanologist and a research fellow at ESA. And I'm here to talk on behalf of the Sample Analogue Curation Facility, which is a relatively new facility of ESA and is based in the UK at the ECSAT site. And so the Luna facility, which is currently being built in Cologne, was already mentioned in the last days. And so in a nutshell, it is going to consist of a huge test bed containing a MARE simulant, and there is going to be a smaller chamber containing a Lunar Highland simulant, and I would like to talk about the selection process and the updates on that. Just shortly about the mission of the SACF. So is to be a European focal point for the curation and the characterization of different simulants. And the aim is to provide expert support on simulant topics for different research and technology projects across ESA and across the European countries and ESA member states. And so how do we achieve that? Well, with research and development, with strengthening the European simulant scene, by communication and outreach, so creating a link between simulant producers and customers in Europe, and by supporting different projects and missions within ESA or in the member states. And so as the last function based on this, so basically it's the SACF's task to select the right European Highland simulant for this dust chamber at Cologne. So here you can see the requirements. These are the main requirements for the simulant. So you can see that it's required to be, well, 8 to 10 tons in quantity, which is quite a lot. Especially when you consider that the particle size range is quite the fine fraction, so from 0 to 90 microns. That's why it's called the dust chamber, so it's the dusty portion of the simulant, and obviously it has to be within the average Apollo particle size distribution, and also, as it was mentioned earlier as well, it's very important that what is the particle shape. And so for this simulant, it's required to be angular, which corresponds to closely 0.65, the angular ratio of it. And obviously, that is connected to the abrasivity. So if you've got more angular particles, the abrasivity is going to increase. And so after we got the requirements, we did a background check. So that means we did a literature review and also a market check within Europe in terms of the Highland simulants. And here is a quite detailed table about, it's an up-to-date table, so on the available Lunar Highland simulants globally. And so the main point here is there is only 2 European providers who can provide Highland simulant, and one is in Greenland, a company, and the other one is the Technische Universität Berlin in Germany. So after the background research, we built up a characterization plan that is basically the order of analysis on these Highland materials. And here you can see a flowchart. How is this going to happen? So the logic behind it is that we can do some characterization of certain properties at SACF, but we are also going to send to different laboratories Highland simulants, and these different laboratories are going to analyze the same properties And so after these analyses, we are going to get the results from the different laboratories, and we will be able to compare the results, compare the different standardization procedures, the calibration methods, and all of those things that are very important when you evaluate analysis results. So the next step is to do actually the characterization work and then to make a decision, choose the right European simulant for the dust chamber. And just a few comments, we identified certain gaps while we did the background research. And just to mention a few, so there is a lack of communication between European simulant providers and customers. There is a lack of European providers who can actually provide quality-controlled Highland simulants, and also lack of European providers who can provide quality-controlled additional components. These could be minerals, agglutinates, and so on. And there is also the lack of batch control processes and the availability to actually compare the results and the quality of these different analyses. And also there we identified certain terminological gaps as well. So if you have any questions connected to simulants or any rocks within our solar system, then reach out to me, and thank you very much.
A reminder to the audience here that there will be a possibility to ask questions during the Q&A later. You can use the microphone here. And for people online, you can post your questions on the platform to Aliz and to all the other speakers from this session. Our next speaker is Piotr Kulinowski from the University of Krakow. And Piotr will tell us about the Rod Scraper Conveyor as an efficient lunar regolith transportation device.
Hello, I want to thank for the opportunity to perform at such excellent event. I'm Piotr Kulinowski. I'm a supervisor of the Universal Space Team AGH Scientific Lab, and the group of students I would like to present, briefly present, the conceptual project of the Rod Scraper Conveyor as a proposal efficient lunar regolith transportation device. I represent Universec. Universec is alliance of few European universities. It's European Space University for Earth and Humanity. It's an alliance of universities from Toulouse, Lula, Düsseldorf, Luxembourg, and Krakow. And we try to teach, to create new engineers for space. How can I switch the slides? It's, yeah. Okay. Space resource utilization chain, value chain was discussed many times during this conference. And like you see on the slide, a very important element of this chain is transport. Transport is very important in any technological processes. It's like a blood circulation in the human's body. The roadmap outlines for the future shows that initial phase in space resource will be primarily used for acquiring rocket propellant from the lunar regolith, which means that the lunar regolith will be the first raw material which will be transported and processed in technological processes. When we design any transportation system, the first step is to identify the properties of transported material. What can we say briefly about regolith? Briefly, because before my presentation, you heard a lot about it, but most important permanent bulk density is about 1,500 kilogram per cubic meter. is highly cohesive and exhibits poor flowability. Its angle of repose in lunar conditions will be over 58 degrees or higher. And what is very important from the point of view of designing a transportation device, it's a fine lunar dust has pretty small particles, smaller than 20 microns, and is very abrasive and electrostatically charged. Next step in the designing process is to determine the ambient and operating condition for our transportation device. What can we say about working condition on the moon? It's a pretty harsh conditions. Temperature in the range 60 up to 230 Kelvins. Gravity pretty low, 1/6 of Earth gravity. Vacuum, and what is very important, a lunar dust can travel a long distance when it's disturbed. So how to do transport lunar dusty lunar regolith? We are focused on the stationary transport. It means that we focus on conveyor. And which conveyor we should to select for this transportation task? Usually, loose materials can be transported using conveyors by carrying or sliding. I got information only 2 minutes, as we will talk faster. We have two ways. One is that we can carry material on the boat. I'm focused on disadvantages of this specific transportation device. It's my personal opinion. It's the point for discussion after presentation. We can support the belt, but it's not possible because we have no elastic string like belts, cables, because extremely low temperature. A lot of kinetics are sensitive to dust. No, we cannot use apron conveyors because also dust-sensitive hinges and heavy plates and heavy structure of conveyor. On the other side, we can slide material on the surface of screw with using vibrating conveyors. But in this point, we have a problem with rising the dust deposit on the outer surface of screw. And also, we will have a problem with large mass fixing the conveyor frame. We can use rotating screw, but in this case, we have problem with crushing, mixing, and high power consumption because of that, and also significant wear of conveyor auger. And also moving scrapers, but with the chain, we will have a large structure. And what can I say? Our proposal, Rod Scraper Conveyor with rotating rod, does not have this disadvantage what was mentioned before. Few words about features of this conveyor, but now I would invite my co-workers, my students, to the stage. And they show you the model of Rod Scraper Conveyor. And what can I say? The material is portioned by scrapers, the motion is smooth, and we reduce the dust generation because optimizing process of shape of scrapers. Now I give the voice to Mateusz, and he will continue presentation. Finally, you start with features of Rod Scraper Conveyor and continue.
So the most important features of solutions are no dust-sensitive kinematic parts, ability to work in the abrasive regolith, and through from regolith in this true technology. And it's designed to convey lunar regolith horizontally and an angle up to 20 degrees. And what's the record? It's a tandem of lunar regolith conveyors. The first one is Rod Scraper Conveyor described before, and it's connected to the bucket elevators, which allows us for a smooth transport of material between them and without the loss of the material. Our project wasn't made without purpose. 1 year ago, Colorado School of Mines started organizing a competition over the Dusty Moon Challenge, which consists of 2 phases. First one, design for the moon, and the second one, prototyping and test on the site. We did a great job. Torrecon took the 2nd place, and also in the next month we are going to the Colorado again to take part in the competition once again with a new version of our device. And thank you for your attention.
Thank you very much to the team at the University of Krakow. And our next speaker is also a well-known face in the community, was here last time. It's Hannah Sargeant from the University of Central Florida and the University of Leicester. And she will tell us about IC simulant for permanently shadowed region. Welcome, Hannah.
Hello, everybody. So I'm presenting some work today that was carried out in my previous role at the University of Central Florida. For those of you who have been using LHS and LMS simulants, they are produced at Exolith Labs, which is actually a lab associated with and kind of supported heavily by the University of Central Florida. So I've been working a lot with that team, using their simulants for different ISRU technology testing. And then also we wanted to look at, can we make icy simulants? And also, just to stipulate, this is work mostly carried out by a master's student, Carl Schlumber, and his thesis will be being published very soon. Okay, so icy regolith simulants. Those of you who want to be going to the polar regions of the moon, investigating icy deposits, harvesting icy deposits, you want to be able to test your technologies, and preferably in a high-fidelity simulant environment. But it's quite difficult to make these to a high fidelity in reproducible batches. At the top here, we've got some examples from Perrington et al. On the left-hand side, we've got ice granules that have been crushed up and then combined with simulant, so they are still quite separate grains. In the middle, we have a technique often referred to as the mud pie technique, but literally mixing liquid water with simulant and freezing it down. And then on the right-hand side, we have ice that has been deposited on the surface. So you have like this solid icy layer. But the problem is, those people who generally develop technologies heading to polar regions, mining these deposits, don't also want to be spending significant efforts and finances in producing these high-fidelity simulants as well. So quite often, they are tested in paint cans filled with simulant, water, and frozen down. Sometimes this can have quite a cement-like physical property, which isn't really what we're expecting to see when we head to the poles. So maybe this isn't really the technique that we should be using. So we had an idea to try and use atomization to mimic the volatile deposition that we think is happening on the poles of the moon. And all this basically means is that we have these tiny water molecules in a very fine mist, and then we allow our simulant to fall through this mist and into a tray of liquid nitrogen at the bottom. And eventually, that liquid nitrogen will boil away, leaving behind a frosty simulant, cryogenic temperatures, and it's really quite fluffy, not this cement-like material that is often used. Here we have an example at the bottom. This is actually a 30 weight percent mix here, so 38% of water with simulant. Now, often anything above 20 weight percent would be saturated if you tried to mix it in ambient conditions. So we can still have quite a granular mix, even with quite high water contents. So most of the time of this project was spent kind of developing the hardware to really get the simulant produced. But there were some initial studies of their properties. The main thing is that this technique produces really high porosity regolith simulant. And we think that the polar icy regolith is actually quite porous, so this was really quite nice. And it seems to be a product of the process itself. So it doesn't matter how much water we add, it will always have this porosity of about 60 to 70 weight percent. So this plot at the bottom, I know it's not easy to see for those in the room, but at the bottom we have our water ice content, and on the left-hand side we've got the porosity, and we've got in green and blue our 15 weight percent and I think that's about 20, 22 weight% respectively. And within each batch, it's actually quite homogeneous, which was quite nice. And so we've got this 60 to 70% porosity here. And then what we did once these simulants were produced, we then dried them out in an oven. And this, the top image with the vials of the simulant, that's it just after being baked out. And underneath is what they look like once we've shaken them, once they've been agitated. And what we found is that the simulant maintains its porosity even once the water is removed. So, for example, if we go to a PSR and we think there might be ice deposits, but perhaps there's been some thermal changes there, that water may have been released, the regolith still might be quite porous. We don't know. So it's just something to consider, that until it gets agitated, the porosity might still remain. So some of the conclusions of our work, we can make reproducible icy simulants, and this is all done in ambient conditions. But it could be done ideally in a dry environment, at least, to stop additional atmospheric water condensing. But the material has high porosity, and the water content can be carefully tailored and controlled by changing the simulant flow rate or water flow rate. And it can be absolutely scaled to large batches. And this is just an example of the properties and the flow behavior. You know, it's quite loose. So that's our simulant. Come chat to me if you'd like to know more. And also just to mention, now based at the University of Leicester, working with radioisotope power systems. So any of you who want to survive the night or have some thermal or electrical power in your PSR exploration activities, come chat to me about that too. Okay, thank you very much.
Thank you very much. Thank you, Anna. I think most of us would like to survive the night, so we'll get back to you. And our last speaker for this session is Susana del Carmen Fernandez, who is online. Susana, can you hear us?
Yes, I hear you.
Yep. So Susana is from ICTEA, University of Oviedo, and she will tell us about exploring mining resources of the moon regolith, specifically lithium. Susana, the floor is yours.
Okay, I will try to explain our study about the distribution of the concentration of the lithium in the lunar surface. Next slide, please. We used 8 samples from the different Apollo missions, and in 2006, Magna et al. Analyzed 2 types of lithium in several samples from the solar system, and for astrophysical purposes, but at least 8 samples was from the moon. We used this information together with the spectral library from geological of these samples, taking in the geological using principal component analysis, and obtain 5 types of spectra from the lunar samples. In blue, you can see the spectral corresponding to the orange and glassy soils. This unit is very important in this study because correspond to the regolith weathering by cosmic ray, lunar regolith weathering, and this unit are enrichment in lithium. Next, please. This work needs an GIS environment, and we use QGIS. The first work in QGIS was georeferencing the lunar samples. Then we downloaded the Clementine imaging from the PhD Orbital Data Explorer. Clementine imaging have 11 bands, spectral bands, 5 in the visible and near infrared, and the other in the infrared. But using the spectral types, we calculate 5 spectral ratio for the lunar samples and translate this information into the Clementine bands using the raster calculator of the QGIS. Then cross the lunar samples with these 16 spectral variables and obtain the values of the system variables for each of the lunar samples. Next, please. With this data, we carry out two linear regression models, one for the total concentration of lithium and the other for the lithium-7 isotope. We extended this model using the raster calculator of the QGIS and the Clementine imaging and obtained two maps, these two maps. But for me, the most important result of this research are related to the distribution of the lithium-7 isotope. One of the important result was the importance of the orange and glassy soils variable in the linear model of the lithium-7 isotope. And the other important result for me is the relation between the topography and the distribution of this lithium-7 isotope. As you can see in the imaging, the lithium-7 isotope are distributed in the in the highest part of the relief of the moon, and the distribution is more intense, more high in the areas very cratered and exposed to the lunar cosmic ray. Okay? Thank you very much.
Thank you. Thank you, Susana, for this well-focused presentation. Unfortunately, I have to eat my words. There won't be any Q&A session for this session. We are already running a little bit late. The next session as well will not have a Q&A, but you are very welcome to either approach the speakers during the breaks or post your questions on the platform. So we move on to the next speaker. It's Igor Drozdovskiy from the European Space Agency's ESAC Center in Madrid. And Igor will tell us about identifying minerals for the Pangea Mineralogical Database and multispectral classification.
Thank you. Just a small correction, I work at the European Astronaut Center in Köln, not in Madrid. Our information is correct. I work as an expert scientist at the ESC, and in this role I support development of a Pangea analytical toolset, which is the subject of this talk. The goal of this project is actually to develop a set of software and hardware tools in order to enable real-time and accurate classification of geological materials on the field. This is a team's effort. I'm only the person who is coordinating this effort. And our Caves and Pangea team consists of scientists, software and hardware developers, instructors, and also experts in ground support for human and robotic exploration, both in space and here on Earth. In our view, an accurate real-time mineralogical analysis would be critical for future missions to the Moon and in other celestial bodies, and both for future human and robotic exploration. Moreover, we are already testing our analytical toolset during the Pangea training that we actually conduct for astronauts, but also for ESA mission developers. And we do it since we are using from very beginning of a Pangea training analytical tools such as portable spectrometers, mostly commercial off-the-shelf products. But we, in order to enhance this kind of products, we developed our own toolset, how to effectively use it on the field. What is our Pangea field activities have shown us that in order to develop, to make this recognition of planetary minerals, first of all, accurate, and at the same time, very accurate, the portable spectrometers, calibration data, meta-information, or additional petrographic information that allows explorers to interpret recognition results needs to be developed together. And this is what actually the loop is actually trying to show. And in our view, is designing and testing together, these tools will provide the necessary accuracy and speed, both for actually recognition of these materials, but also in sharing this information on the importance of these discoveries, both to the field, to the crew on the field, but also to the science support room. So our mineralogical toolset consists primarily of two main products. First, it's a catalog of petrographic information, which includes information on all currently known minerals on Moon, Mars, and asteroids, and proxy of asteroids are meteoroids. But we also include spectroscopic information. So for all these minerals, what we are currently known exist on these planets, we actually looked for all the available spectroscopic information. And here we focused originally on the molecular spectroscopy. Therefore, in our catalog, most of the data comes for the reflectance, visual near-infrared spectroscopy, but also for Raman. And then we also added to this also atomic spectroscopy. And this catalog and the spectral archives serves as a base or reference data set and reference meta-information for our own machine learning development, which is actually, there is a flow chart shown on this next. In our understanding and our field experience, the best results we are getting when we are actually using multiple different spectroscopic methods. At least what we're trying to do is to combine molecular and atomic spectroscopy. Molecular spectroscopy, as I mentioned, we can directly evaluate from geological materials using reflectance and Raman spectroscopy. But for atomic spectroscopy, we also started to use X-ray fluorescent and laser-induced breakdown spectroscopy. Using machine learning methods allows us to fuse this kind of data to make better predictions. We are actually able to do the information on the individual minerals or end members, but we also started to employ spectral mixing using machine learning methods in order to evaluate also mineralogical composition of the compounds. And these two products we already have been tested on the field, as I already mentioned, and for this we integrated our both catalogs, reference information, and our machine learning models and all additional information into another tool set that have been also developed in our team, which has a name, Electronic Field Book, that have been already presented in this meeting last year by Leonardo Turchi, who is also present here. In our current efforts, we are further improving, first of all, our reference data sets, which is critical for machine learning classification. We also tuning our models, and what we also started to do, we are starting to work also on the better integration of all of this within the electronic field book. Finally, we are also supporting the industrial contract that have been awarded to the consortium. It was and funded by ESA to develop combined spectroscopic portable instruments that can actually benefit in co-aligned measurements of the geological materials here on Earth, but also on the Moon. If you have any interest in this topic, you can look on the references which are shown on the top right screen, or just directly ask me any questions. Thank you for your attention.
Thank you very much, Igor. And now we give the floor to Yue from Imperial College London. And you will tell us a little bit about the theory for particle motion in electrostatic traveling wave fields.
Thanks for the introduction. I'm grateful for having this opportunity to share my work with you. First, I would like to thank the supervision of my supervisors, Catherine, Yang, Stan, and Yang Hua. and thanks for the funding support for my travel to Luxembourg by UK Space Agency. Today I'm going to talk about the theory of particle motion in electrostatic wave field. This is a potential application for the beneficiation process of ISRU. Electrostatic wave is a technology that can transport and manipulate particles due to the electric forces on them. As we can see in the right video, these white powders move fast on the screen board. This technology is particularly well suited to the space environment due to the lack of moving parts and absence of moisture. The key part of this technology is a series of parallel electrodes underneath the screen board. The connections and positions of electrodes can be illustrated in the left photo. We can see here that every other 3 electrodes are connected to one point. So there's 4 groups of electrodes. The 4 groups of electrodes are connected to the 4 output channels of the high voltage output. So this is a 4-phase traveling wave. Here we use the function generator to control the output of the voltage, like the amplitude, frequency, and waveforms. In this way, we can use the function generator to control the particle motion in this field. In order to better understand how particle acts in this field, we have done controlled single particle motion experimental research. By using high-speed camera, we have observed 3 motion modes clearly. Here I will introduce it in detail. There we can see 3 different color trajectories. For the smallest particle, which is in yellow, it can be navigated in a certain height without falling to the surface because the particle height is confined in a certain range, so it's called curtain motion mode. As particle size becomes larger, it only can navigate it close to the surface where the electric field is strong. As it's navigating away from the surface, the intensity of electric field drops quickly. Therefore, it will drop down. This alternating falling and bouncing movement is called hopping mode. When particle size becomes even larger, it may only move along the surface without navigate in a certain height. It's like people surfing along the sea wave, so it's called surfing mode. In conclusion, that by doing the experimental research, we have clarified particle motion in this field. By using the different navigation height or different motion directions, we can make use of this to separate particles with different sizes and properties. In addition to the experiment system, we have built a physics-induced model to calculate particles' movement trajectories and their movement average velocities. Okay, sorry. I will be quick. From the photo, we can see this is a result of the relationship between particles' movement velocities and their particle size and operating frequencies of the system. The z-axis is the movement velocity. From the photo, we can see that at lower frequencies, particle tends to move faster. And also, we can see at a critical frequency like 60 Hertz, some people may move backward for the big particles. For the deep blue part, the particle has negative velocity, so big particle move backward. And for small particles with the red part, small particle can move very fast in the forward direction. By using the different motion directions, we can successfully separate particles effectively. And we also did a separation test using Baltini particle. It's kind of glass-based, and we get high separation rate and recovery. In conclusion, we have done experimental research to clarify particles' motion modes. And also, we built a physical model to estimate and analyze particles' motion in this field, which can also allow us to predict the performance of the system in the space environment. Finally, our model can guide the design of the system for different applications. such as the beneficiation process of ISRU. Thank you very much for your attention. Welcome to contact with me. Thank you.
Thank you very much, Yu. Now we have a couple of talks on artificial intelligence. A lot of digital technologies here. The first one is by René Prissang from the Free University in Berlin. And René will tell us about operative deposit modeling using artificial intelligence as a tool for future space mining.
Thanks a lot for your introduction. Ladies and gentlemen, I've learned at the conference that autonomous technology for rovers, for mining machinery had made tremendous advances. However, geological modeling was a little bit off topic, so that I'm very happy to provide you with a useful tool for future space mining ventures, and this tool I call operative deposit modeling. So the basic idea is in any mining venture, when we do planning, we have to take decisions. Decisions are based on a predictive geological model, which has to be evaluated to decide if a block shall be transported to the beneficiation plant, if it should be transported directly to the tip because it's not worthwhile to investigate and to take the property under consideration out. But there's a big drawback that our geological model will be outdated after a short time of operation. With any block mined, we do not even mine out material, we mine also knowledge. So the basic idea is that we can update our model frequently using these data from the mining operation. The entire idea is called operative deposit modeling, and it is a rolling forecasting scheme which supports the rolling mine planning activities. The system is highly automated, can run in fully automated mode, and I think, therefore, it is well suited for use in autonomous mining systems. Here, a short overview of a possible lunar or Martian mining activity. Upright, a mining block excavated, for example, by a razor-type excavator. We have seen it in this conference already, which is followed by a cube rover taking ground truths, providing positional information, providing quality information, for example, by X-ray fluorescence analysis, and grade values, positions can easily be transmitted to the base station, to the lander, where a computer can, at a given interval or during lunar nighttime, or when the computer is not needed for communication, update the complete model so that for the next, in quotation mark, shift of the razor, there's a new geological model supporting new mine planning decisions. So we have a software solution developed. This is a linear octree-based geological modeling system. It's an open toolbox, Linux-style programs, fully generic. They can be glued together using any scripting language, could be C shell, bash, Tcl, whatever you like, to form finally a given, to form a given operative deposit modeling system. Currently, the system covers all the necessary features for deposit modeling, model generation, estimation, kriging, inverse distance, universal kriging was now this year enlarged by Markov simulation, and we have different evaluation tools like classifications or connected component labeling. Yeah, you see the entire size of the system is very small. 2.5 megabytes are taken up by the executables, so it can be easily fit on any computer, on a lander, or even on a rover. Yeah, finally, 2 words. Programs have been developed in the framework of 2 European Union-funded research projects, so they are available for anybody to use. And we talked in this conference also about the technology readiness level. I think we have reached it. The system is in operation since over 25 years in Austrian magnesite mine. And it's not only in operation, it is also constantly monitored if the prediction performance, which was initially stated, is kept and reached. And we are happy to deliver this information. So if you're interested, I could show you the system. Thank you very much for your attention.
Thank you, René. And as the last talk for this session, we have another take on artificial intelligence to enable human and robotic exploration and resource utilization. And it will be presented by Cristina Luna and Alba Guerra from GMV.
Great, thank you. Good afternoon, everyone. Thank you, Advenith, for the presentation and the session. And thank you, Igor, you and René, for the very interesting presentation you have given. It's an honor for me to be here today presenting the work that we are developing in GMB in relation to space robotics. In this case, I come to show the work we are developing in the ISRU project, a project co-founded by ISA and GMB in relation to how to enable the extraction and use of planetary resources in a collaborative way and powered by AI. I have seen that the lunch is here, so already on the table, and I imagine that you will be hungry, so I hope that the wait works. Perfect. Great. But first, let's talk about the current picture. We are in relation to this future scenario where humans and robots need to collaborate to enable our expansion into space. Currently, many missions from space agencies such as ESA, NASA, or JAXA are focused on developing the future space rovers that one day will be able to perform many things on the moon and beyond. In fact, we have even demonstrated with the European Moon Rover system that we will be able to excavate in the moon during the field test that we developed at DLR last January. These space rovers and other kind of robots will perform the first tasks that will help us to live on the moon, and one day maybe Mars. At this conference, we are fortunate to be able to see many of these awesome projects that all of the colleagues are presenting, and connect with people from different companies and institutions to make this community that will enable our next steps in space. At GMB, we believe very strongly in sustainable and inclusive space resources utilization, space exploration, and in cooperation with key players in the space industry, and especially in the European space industry. And that is why we collaborate so closely with ESA in robotics, in projects such as the aforementioned EMRS or in ISRU, the project that concerns us today. As You may know ISRU projects involves many technologies, many different actors, many strategies, and so requires this project. In this project, we are developing different modules for navigation, perception, manipulation, multi-agent capabilities, and also cooperative behavior. It's such a big project, and we have little time, so we are today focusing on a very specific part of the project. Perfect. ISRU, which actually is an acronym for AI-enabled robotic software suite for autonomous collaborative ISRU. It's better, the acronym. Aims to create a software suite that enables collaboration between robots and astronauts in complex ISRU scenarios. We are focusing in this collaboration between robot-robot and astronaut-robot into concrete scenarios for the project. The first scenario is the resource terrain identification carried out by 2 rovers, and another space collection and manipulation, as well as repair of lunar bases that we demonstrate with the other use case is the solar panel repair with astronauts. Keep in mind that the main goal of this project is to create a software suite that is abstract and transparent for any platform that is using it. So the project is not specifically focused on one use case or another. The first use case, the resource and terrain identification, involves 2 mobile platforms, Lamar and May in our case. The leader robot, Lamar, be the one on the left, is equipped with some scientific tools. In our case, we are using spectrometers and high-res cameras, and a robotic arm equipped also with a tool changer that is able to change some tools and get some samples. Lamar will be mapping around the terrain, identifying the terrain, while May, the second robot, is equipped with other tools, and regolith and samples container will be supporting the leader robot. Once Lamar finds any interesting feature on the terrain, it will send an alert to May, the second robot, so May can come to Lamar and help them with the tools, the regolith container, and whatever it needs. In this collaboration, Lamar and May share the tools and share the data. They are able to move planetary resources to the base, are also being able to perform a preliminary analysis of the samples. In the second use case, the one on the right, is focused on the collaboration between astronauts and rovers, considering that in the meantime, we will be cooperating each other. The astronaut will carry a mixed reality device on the helmet, as well as a commander console on the arm. Using both devices, the astronaut can communicate to the mission control, and with the robots also, of course, can see the data that the robots are getting, the alerts, can see also the map that the robots are doing, can move the robots, command, and so on. To demonstrate this, we have prepared a solar power plant mock-up at GMB Spain in our Mars Yaris scenario. With this mock-up, the robot can help the astronaut to repair the solar panels while it's monitoring every time the task and the astronaut's behavior. So the robot can send messages and commands to the astronaut too. For us, there's no ontological difference between robots and astronauts, and not at ISRU software level. And so means a full integration in terms of software for the astronaut and for the robot. Following what astronaut Matthias Møller says yesterday, the future will be a combination of both humans and machines, and we are willing to enable that combination, and all of us are paving the way to it. So this complex task requires a highly developed AI capabilities. We have developed different modules to recognize and segment the terrain, to be able to label the geological features, resources of interest, and objects, as well as you can see in the left pictures, to detect damage on the moon-based infrastructure. And also, we have developed a pioneering module for interaction between astronauts and robots and the environment. So once we can detect the objects, the features, the astronauts, other robots, and so, we can draw some margin boundaries between the astronaut and the environment to make a safe distance for the astronaut, which we were able to navigate between them, and also an avoidance zone for the robots, of course, that will ensure astronaut safety. Right. The problem with AI, well, at least one of the biggest problems, is to have data, quality data, to be able to use our models. So that's why we went last year to ESA's Robotics Planetary Lab at ECSAT to take a data set of images of astronauts, robots, and the environment. Another problem is to label all this data, because you can get a huge amount of pictures and so that unlabeled data. So we use a novel self-labeling system, which we will maybe present another event, that to self-label all the Hue images, avoiding wasting our colleagues' time. Promise, no interns have been hurt during the labeling task. Thanks to this data, our rovers can now monitor the astronaut task and check that they are performing what they need to perform. They are able to interact, detect the interaction with the astronaut and all the objects that are around the environment. And this interaction can be used for many other scientific things, not only in the moon, as well as reducing the astronauts' risk and enable the collaboration between astronauts and robots. But well, this is a technology demonstration, so let us show you our work. Mid-May, our mini autonomous explorator, named after Mae Jemison. Come up with one. Perfect. Mae has come to show you some of the capabilities of our system. Oh, perfect, it's on the big screen. That's perfect. Which we will also happy to show you later during the last break or whenever we will be here around the conference. What will Mae detect? Okay, Mae, as you can see, has a screen to show you what is seen. You may ask, how we are going to show you with our astronauts around? But, well, maybe we have an astronaut around. Maybe, I don't know. yeah, please, give applause to Silvia. We are lucky, okay. By chance, an assistant had an astronaut costume. We promise. She's not an intern either. Okay, maybe it's not a coincidence that we have an astronaut here in the room, but what we can bring, of course, to the Expo, and not yet, I think, is the moon. So today we are just demonstrating Mae's ability to detect astronauts in emergency. I think if you can point to the screen. Wait, if we can wait. Oh, here we are. So, for example, if Silvia suddenly falls on the scenario, oh, emergency. You can come up. You are amazing, Silvia. You have noticed that the screen turns right. You can still fall in. It's funny for us. Now, we have had prepared another thing, but you were talking yesterday about the Space Resources Challenge, saying that you always have challenges in the last time. One challenge, a smaller screen, and a really bigger scenario. So now the screen is just turning red to saying emergency. She's saying emergency. Okay, Silvia, do whatever you want. Yeah. So in that way, even if Silvia, please don't, falls slowly simulating the lunar gravity, it will send an alert so all the robots around there can come to help the astronaut in the environment. Okay, sorry. So thank you so much for your attention. I will be happy to answer your question or chat later if you want. Thank you.
Thank you very much. So I'm turning to the organizers. Okay, so we've recovered the time. Good news. So we have some time for questions. So if I can ask the speakers who are still around to come on stage, and we'll take a few questions. So please welcome the speakers again. And we have a first question online for Hannah, but she's not here. So we have one for René. René, how do you account for the different gravity and weather processes which affect the outcrops in your mining model?
Yeah, hello. This is a problem that we have not yet looked into it. So in fact, my task is property modeling. So having X-ray fluorescence analysis, having a position would be fully sufficient to update the model. Yeah, unfortunately, it's a problem of the rover developers to take care of different gravity, of different atmospheric conditions. So if I got property data, positions, I would be happy and I could update and keep the model on a current state. Thank you.
Thank you, René. We have no more questions online. If anybody has a question to any of the speakers in the room, you can use the microphone at the center of the room. In the meantime, I do have a question for University of Krakow. So you have shown a trade-off between the different conveyor systems for regolith. I think one of the challenges in your case is abrasion and erosion of the materials and mechanism. What sort of materials do you have in mind for your system?
The question is about abrasion and the influence on the work of our conveyor. We decide to, we're testing in laboratory or properties. We use a simulant of regolith and how it behave. And first of all, we reduce speed. We try to move material fluently, smoothly, and we decide to use a special lining material inside tube. It's a special material, but I cannot say too much because we are before competition in Colorado School of Mines next month, and we prepare for challenge. But it's a special material to reduce the abrasion and with a low coefficient of friction.
Thank you. Is there any question from the room? Otherwise, I continue. So for our last speaker, Christina and Alba, I think one of the challenges in AI systems in general is to have enough data sets in order to train your system. Obviously, you have a limited amount of recent data, so how do you cope with that?
It's on? Yeah, it's one of our biggest problems. We are collaborating with ESA to solve this. We are using synthetic images to level all to be able to train the images and also creating almost real data sets to solve at least the most problems that we can have. And then to do this transfer learning to be able to retrain always our models.
Understood. Thank you very much. And we have, I had a question for Kyle. He's not here. So then we move to Piotr, who is here on, no, sorry, not Piotr, to Igor, who is here on stage. So you have told us about building a database for the Pangea minerals, but I would say the set of minerals that you have in the Pangea area is not matching exactly what we expect to find especially in the polar regions. So can you tell us about what critical materials are not expected to be there, and how do you account for that in your database?
So
Our mineralogical database only uses actually the samples that have been identified previously. So we do supervised classification. So original system was not designed to detect not yet discovered materials. However, based on all the remote sensing and the lunar sample data, the mineralogical database currently includes all the known minerals, both on the Moon, Mars, and asteroids. So this is not significant trouble. At the same time, actually, the previous speaker also mentioned that we're also working on how to adapt our algorithms in order to discover new, not yet known minerals. So the idea of incremental learning, few shots learning, we also been testing, and we have some already good results in order to update and do semi-supervised learning in order to do this kind of work in the future missions.
Thank you very much, Igor. And I'm turning to the room again, see if there is anyone who has a question. For any other speakers, no. I think everyone's thinking about lunch at this point. So we have you on stage. So you have told us a little bit about your theory for particle motion in electrostatic traveling wave fields. So there has been a number of models for electrostatic charges on the Moon. I think one of the difficulties is to model the electrostatic charges coming from the contacts between particles. Is that accounted in your model, and how do you validate your model against data?
Yes, thank you. This is a very good question. So currently, we like to keep the charge constant in our model. In the next step, we will need to consider the contacting of different particles and considering the charge transfer. Yeah.
Okay, understood. So if we do not have any more questions, I think we can take, yes, one more. Okay, online. No, from my end, I think, at least for the speakers who are currently on stage, I do not have more questions. I had questions for people who have already disappeared. So yeah, if the audience is happy with everything that has been presented by the people on stage, then I propose that, Lisa, you conclude the session. Thank you very much again to all the speakers, and Lisa.